Okay, so last time, as I mentioned, we started talking about acids and bases. Remember, the basic definition of an acid is something that can produce H plus ions in solution. And remember that when we were sort of talking about acid and bases, when we talk about H plus and H3O plus, which is the hydronium ion, they're essentially the same thing. So again, as we talked about last time, pretty much anywhere you see H plus, you could put in H3O plus and vice versa. I personally use H plus a lot of the times, but a lot of books and stuff will use H3O plus. So they pretty much are interchangeable in sort of acid-base chemistry. Basically, the H plus or H3O plus represents really sort of the acidic part of the solution. And a base is, the general definition of that is something that's able to produce hydroxide ions in solution. And again, what we were talking about in terms of this is really in the case of an acid, able to produce H plus ions free floating around in the solution. And in terms of a base, able to produce OH minus ions that are freely floating in the solution is pretty much what makes those guys either an acid or a base. We talked about a little bit more of a general definition of acid and bases, and that is the Bronsted-Lowry definition. And really in the Bronsted-Lowry definition of an acid or base, an acid is a proton donor. And really a proton is an H plus. And that's again because hydrogen has a proton and an electron and no neutrons. So when it loses its electron, it becomes an H plus. It means it only has really a proton left. A base, on the other hand, is something that will accept a proton. And basically, sort of the consequence of Bronsted-Lowry definition here is we do end up with some partners on opposite sides of the arrow. So when we have an acid plus a base, again, acid really donating the H plus over to the base, we create something that's known as the conjugate acid and conjugate base. And these guys on the right-hand side of the arrow are basically related to the ones on the left-hand side. So our acid on one side, its partner on the other side is the conjugate base. And because the acid will donate that H plus, the conjugate base will have one less H plus when it's all said and done. And our base on the left-hand side there is basically partnered up with our conjugate acid. So our base here is partnered up here with the conjugate acid. And since the base is really the thing that will accept an H plus, we do see the conjugate acid having one more H plus than its base sort of counterpart. A reminder that kind of your run-of-the-mill acid and bases on the left-hand side of the arrow there, all your conjugate guys and partners on the right-hand side of the arrow. The other important thing is it can only be a difference of one H plus. So in order for those guys, again, to be conjugate acid base pairs, the only difference between them is one H plus. We, towards the end there, started talking about water, and water actually will react with itself. And there are things, as we talked about too last time, that can act both as an acid or a base. So the same thing can act as either an acid or a base. And those are things that are referred to as being amphoteric. And in the case of water, it actually sets up an equilibrium, and we get what is referred to as Kw, which is the concentration of H plus times the concentration of OH minus, and that equals 1 times 10 to the minus 14. This again is basically the acid part of the solution. This is basically the base part of the solution. And we could use this Kw equation, which you always have in terms of that number, and we can solve for one or the other. If we do know, for example, the OH minus concentration, we could take 1 times 10 to the minus 14 divided by the concentration of OH minus. Remember, when you see brackets like that, that means concentration. And basically what that means is molarity, which is moles per liter. You could also do the same calculation for the OH minus, exactly the same. It's 1 times 10 to the minus 14 divided by the H plus concentration. And you could use those values that you get to basically determine, is the solution acidic, basic, or neutral by comparing the two. So if you compare the H plus concentration and it's greater than the OH minus concentration, that basically means that the H plus, or the acid part, is larger than the base part. And that means that this solution would be acidic. If you got the H plus concentration and it actually equaled, or fairly equaled there, the OH minus concentration, that means they both would equal 1 times 10 to the minus 7. That would be a neutral solution. And lastly, if your H plus concentration was less than your OH minus concentration, that basically means that the base part of the solution is larger than the acidic part, and it would be a basic solution in that case. Remember a couple of things important here. Definitely using your exponent button, really important, when you are punching these numbers in. Also really important to remember when you go to compare the H plus to the OH minus, and you have a number that is like -7, 10 to the minus 7, or a number that's like 10 to the minus 2, it is actually, again, the smaller negative exponent that is larger than the larger number. Again, the negative is important there. That means we're going 7 places this way and making a much smaller number than only going 2 places this way, which would be a much larger number. Any questions on any of those things that we kind of talked about the other day? So I think we did a couple of examples last time. So let's see what we got going on next here. Somewhere. All right, so let's kind of change this around a little bit here. Let's not really answer what it's asking. Let's go with what is the OH minus concentration. So find the OH minus concentration and determine, is it acidic, basic, or neutral. So take a moment or two and see what you come up with. Again, just basically calculate the OH minus concentration and is it acidic, basic, or neutral. Concentration, we're looking for the OH minus concentration. So that again is our Kw that we want to use, which again is the H plus times the OH minus, which equals 1 times 10 to the minus 14. Again, a reminder that you can swap out the H plus for H3O plus times OH minus. It's equal to 1 times 10 to the minus 14. Again, both basically the exact same thing. Again, I typically use H plus, so we'll use that one. We want to solve for the OH minus concentration, which means we're basically going to divide the H plus concentration to the other side. It gives us 1 times 10 to the minus 14 divided by our H plus concentration, which gives us 1 times 10 to the minus 14 divided by 2.8 times 10 to the minus 5. Again, a reminder that when we put this into our calculator, we want to use our exponent button. So again, you would hit 1, your exponent button, your negative button, and 14, hit your divide button and type in 2.8. Again, your exponent button and your negative button and 5, and obviously hit equals. And if we do that, looks like we end up with 1 exponent button minus 14 divided by 2.8 exponent button minus 5. Looks like 3.6 to the minus 10 is the answer that we end up with. We do need to put molarity next to it since it is a concentration so that we have the proper units. First off, any questions on that calculation there? So now that we have the OH minus concentration, and obviously we have the H plus concentration, we basically want to compare both of those numbers. And we want to look at the H plus concentration. We want to look at the OH minus concentration. And we really want to see basically which one is larger. So our H plus concentration is 10 to the minus 5. Our OH minus concentration is 10 to the minus 10. That means in this particular case, the H plus concentration is larger. Again, the minus 5 means we're only going 5 places this way. The minus 10 means we're going like 10 places this way and makes it a much smaller number. And because the H plus part is larger, that basically means the acid part is larger than the base part, and that makes it acidic here. Any question on that? Also, an important relationship that we also talked about is the relationship between H plus and OH minus, and it's basically an opposite relationship. So if the concentration of H plus increases, concentration of OH minus will go down, and vice versa. If the H plus concentration goes down, we will see the OH minus concentration go up. So they are always sort of tied to each other, which is an important idea. And basically, as one goes up, the other goes down. So they are always sort of related to each other. Any questions on any of that calculation there? All right, let's try another one here. And again, we'll do something different here. Let's just go with the OH minus concentration again. Forget about how many times greater. Let's just solve for the OH minus. And again, alrighty, so again, really the good news is in terms of these calculations, these particular ones, it's really the same calculation, really, regardless of which one they give you. In this particular case, again, they gave us the H plus, which means we could solve for the OH minus by using KW, which again would be 1 times 10 to the minus 14 divided by our H plus concentration. Here, putting in our numbers, divided by 1.0 times 10 to the minus 9. And again, we would go with our 1, our exponent button, negative button 14, divided by 1, exponent button, negative button, and 9. And we end up with 1 times 10 to the minus 5. In this particular case, if I can find my pen here, where'd it go? There it is. 1.0 times 10 to the minus 5. Again, we do need the molarity there as it is a concentration. Again, looking at our H plus concentration versus our OH minus concentration. And for the most part, you really can just look at the exponent part to help you make that decision. So when we look at the OH minus, we see it is to the minus 5. And when we look at the H plus, it is to the minus 9. Again, the smaller negative exponent is the larger number, which means in this particular case here, the H plus concentration is actually, let's try that. The H plus concentration is actually larger than the the OH minus concentration is larger than the H plus concentration, and that would tell us that this is basic. Any questions on how to use KW or punch it in? A reminder that basically you want to make sure you use your exponent button, and it's basically kind of the same calculation. Okay, then let us continue on and talk about actually the pH scale. So very commonly, we do use basically the pH scale to help us determine if something is acidic, basic, or neutral. And the pH scale basically runs from 0 to 14, where below 7 is basically acidic. So our pH scale goes from 0 to 7 to 14. Below 7 is acidic. Above 7 is basic. And dead on 7 there is technically neutral. And when we look at 7, 7 is sort of our middle point, if you will. And as you go from 7, that closes, get out of my way here, right. Thank you. As we go from 7 down towards 0, we are becoming more acidic. Get this thing out of my way here. Keeps getting in my way. There we go. More acidic. And as we go from 7 towards 14, it becomes more basic. And again, 0 through 14 is basically what we look for in terms of acidic, basic, or neutral. How do we calculate the pH? Well, the pH is calculated through this formula right here. pH is equal to minus the log of the H plus concentration. Again, the actual name tells you what you need. pH tells you that you do need the H plus concentration to calculate that. Again, much like we've been talking about, you could also put in H3O plus, which again is the same thing. Now, to use this formula here properly in your calculator, again, we're going to use our log button here, but it depends if you have a display calculator or again, a non-display calculator as to how you should properly punch these in. If you're not sure, you actually can hit your log button. And if you hit your log button and it says log, you have a display calculator. If you hit the log button and it says error, you have a non-display calculator. So if you have a display calculator, you basically type everything in exactly the way the formula is. You hit the negative button, not the subtract button, but the negative button, the log button, and type in the H plus concentration, probably using your exponent button. If you have a non-display calculator, this one and all the rest of the formulas we're going to talk about here today, you need to go backwards. You need to start with the number, then hit the log button, and then hit the negative button. So again, depending on which way you go, as to what you would need to do. Now, let's talk a little bit about significant figures here and the pH. So the number of decimal places in your pH value should equal the number of significant figures in the concentration value for the solution. So what we're talking about here is going from number of significant figures in your concentration to number of decimal places in your pH. So why don't we try one here? Make sure, again, your calculator works. So let's say we had an H. Okay, so let's take a look. First off, let's talk about calculating the pH before we actually talk about sig figs. Make sure we're all on the same page, again, how to do that. Again, the pH here would be equal to minus the log of the H plus concentration. They obviously gave us the H plus concentration, so we would go minus the log of 1 times 10 to the minus 5. And when you put that on your calculator, again, if you have a display calculator, negative button, log button, 1 exponent button, negative button, and 5, and then equals. You should get a 5. It's probably staring at you on the screen there. First off, any questions on how to punch it in? Again, if you have a non-display calculator, you would go with the 1 exponent button, -5, hit the log, and then hit the negative button.
Professor Efron, I got a -5. Is that because I didn't put the negative before the logs?
I'm assuming you have a non-display calculator, so you started with a number.
No, I have the log button. I push in. It's a log in a parentheses, and I punch in the information.
It's probably because you missed the negative there at the beginning.
Where would that go? Before the word log?
It would. So if you have a display calculator, you would actually hit your negative button first, and then you would go hit your log button.
Oh, okay.
And then type the rest in with, obviously, like we've been doing with our exponent.
Yes. Okay. Awesome. Thank you.
You're welcome. Other questions? Okay. So the pH here is 5, but we want to make sure that we do record it to the proper sort of significant figures. So we have a couple of options in terms of how we should record this guy. We could go with 5, maybe 5.0, 5.00, 5.00000000. All right, so hopefully that's probably the wrong one there, since I'm running out of room there. So let's see what really, again, the significant figure rule says. What the significant figure rule says is when you look at the concentration value, which is this value right here, we want to look at how many significant figures that number has. And in terms of significant figures, if we look at it, a number in scientific notation, these numbers right here are significant, which means the concentration value has 2 significant figures. Now, very often confused is that has 2 significant figures, so I should have 2 significant figures in my pH value. But what it means is it's actually the decimal places, which means it actually should be correctly written as this one. The 2 significant figures here correlate to not the 2 significant figures here, but the 2 decimal places. So 2 significant figures gives us 2 decimal places when you're going from concentration to pH, and vice versa. We're going to talk about going the opposite way. So if you happen to have started with the pH value of 5.00 as 2 decimal places, which means if you were going to calculate the concentration from it, you should have significant figures. So here we're looking at going from sig figs to decimal places, and vice versa if we're going the other way, decimal places back to sig figs. Question on that there. So obviously this would not be the correct way to do it, nor would this way. Again, significant figures to decimal places. And talking about, is this acidic, basic, or neutral? If you do have the pH calculated for you, you should always use the pH to help you determine, is it acidic, basic, or neutral? And obviously, with a pH value of 5, which would be about there, it is obviously less than 7, which means this guy would be an acidic solution. Any questions on that there? All right, let's try a couple more here to make sure calculators and all that good stuff is working. We got one coming. There it is. All right, so 2 separate problems here. What is the pH value for each of these? So see what you come up with. We're looking for the pH value for each of these 2 different problems. So you should come up with 2 different pH values. All right, take a Okay, let's take a look and see. So we're looking for the pH here in both cases. Here, we'll go that one. So look at number 1 there. We can calculate the pH. Is equal to minus the log of the H plus concentration. In this case, they gave it to us, so we are good to go. Minus the log of 2.1 times 10 to the minus 5. Again, making sure that we do put that into our calculator correctly. So I have a display calculator today. So minus negative button, not to subtract, log 2.1, exponent button, negative button, and 5 gets us a 4.68 pH. Now, again, in terms of how to take our answer in terms of pH, we look at the concentration here. Concentration has 2 significant figures. Our pH, again, not significant figures, but ends up with 2 decimal places in that case. Any questions on that one there? Now, looking at this as well and looking at our pH scale, which again goes from 0 to 7 to 14. This again is below 7, which means that this guy would be an acidic solution. All right, looking at number 2. Again, we want the pH, which is minus the log of the H plus concentration. Again, the name tells you what you need, and that's important to recognize that we actually do not have the H plus concentration given to us. We have the OH minus concentration, which means we can use KW to get ourselves over there to the H plus concentration. So the H plus concentration would equal 1 times 10 to the minus 14, which is our KW value, divided by the OH minus concentration, gives us 1 times 10 to the minus 14, divided by 5.9 times 10 to the minus 8. And if we do that, gets up there, 1 exponent button negative 14 divided by 5.9 exponent button negative button 8 gives us a number of, we'll call it 1.7, I guess. Oops, 1.7 times 10 to the minus, a lot of zeros, 1, 2, 3, 4, 5, 6, 7 molar. Now that we actually do have the H plus concentration, we can go into the pH here. And that would now be minus the log of 1.7 times 10 to the minus 7. And if we do that there, you get something like 6.77 as your pH value. Now, that also is slightly below 7. So that is what we would call probably slightly acidic. Again, technically speaking, neutral being exactly 7 at that particular point. Now, if you weren't perhaps careful, and by the way, we do the same thing here in terms of decimal places. Again, we got 2 sig figs here, and we end up with 2 decimal places here. If you weren't really careful, you just went into the pH equation using the OH minus concentration, and you thought you got yourself a pH of like 7.22-ish, something in that ballpark. You didn't calculate the pH because you used the OH minus concentration, but the good news is you calculated what is known as the pOH, and that is basically calculated the exact same way. The pOH, again, tells you what you need is equal to minus the log of the OH minus concentration. So here, if we did that, minus the log of the OH minus concentration, which is minus the log of our 5.9 times 10 to the minus 8, we end up with what you got down there, I think, like 7.23. Sure you got 7.23. And that's not necessarily a bad thing, other than it's really not the pH. But there is a nice relationship between pH and pOH. pH plus pOH equals 14, which means you could actually then solve for the pH by taking 14 minus 7.23. And that yields us our 6.77 pH. So you do want to be careful. You want to be careful that you are using the correct concentration when you go into these, and not just sort of blindly, plugging and chugging into there. And you don't actually calculate the pOH versus the pH. Any questions on that one there?
So, Professor, I came up with the 7.22. So how do you differentiate between using the KW formula versus the pH?
So say your question one more time. How do you?
Yeah, how do you know when you use the KW formula versus because I did it, but I just plugged in the numbers directly and I came up with the 7.22.
Right. So you went in on the second one. It said minus the log of 5.9 times 10 to the minus.
Yes.
So what you actually calculated is really not the pH. It's
Mhm.
what's the pOH. And that's because that's the OH minus concentration. So there is a different meaning for that value. So there's actually several different things. There's the pH, which measures the H plus concentration in solution. There's the pOH, which measures the OH minus concentration, which is really what you calculated when you get to 7.23.
Yes.
And the KW is used to figure out the H plus concentration or OH minus concentration. So those are kind of like, sort of four different things in a sense. So when we talk about KW, it's basically the H plus times the OH minus concentrations. And basically we use KW basically to solve for one of those two things. What is the H plus concentration and what is the OH minus concentration, which essentially tells us in the solution, basically how much H plus is floating around and basically how much OH minus is floating around. We use pH to measure basically the amount of H plus floating around. It's just another way of looking at this number that makes it a much more simple number. Like instead of something times 10 to the minus 7, it gives us a number like, hey, 7, or it gives us a number like 4. So it gives us a more simplified version of it. So really pH is related to the H plus in a way that we kind of make it a more simpler number to sort of quote, like, if you were doing the pH scale or something like that, or told somebody the pH is like 4 or 5, 3.2, something like that, which is a much easier number to sort of understand that that's acidic or neutral or basic than if you said, hey, the H plus concentration is like 2 times 10 to the minus 6. Somebody would look at you and go, I'm not really sure maybe what that means. But turning sort of that H plus concentration into a pH value, most people have in their head the pH scale, which we talked about there, which again, below 7 is acidic, above 7 is basic, and again, 7 there is neutral. So when we tell somebody, hey, the pH is this number, it's really related to how much H plus is floating around the solution. And it's just a more convenient sort of way of expressing, is it acidic, basic, or neutral? And the same sort of thing with when we talk about pOH, it measures the OH minus concentration. It is really related to how much of that OH minus in there. And it really is also, a kind of more simplified way of expressing, is the solution acidic, basic, or neutral, with kind of like whole numbers ish, if you will, go numbers between 0 and 14.
Yes.
Here to sort of understand, then like you tell somebody, hey, the OH minus concentration is 3 times 10 to the minus 14 or minus 12 or something like that. And, they're like, okay, that's nice to know. But you tell somebody, hey, the pH is 9, they know automatically, hey, that's basic and stuff like that. Okay. But we should be very careful as well. You can't calculate the pOH, but the pOH scale actually runs opposite of the pH scale. So the pOH scale is also 0, the 7, the 14, but on the pOH scale, below 7 is actually basic and above 7 is acidic. So they do sort of represent kind of like the same numbers, but they do mean different things if you tell somebody a pH value versus a pOH value in terms of whether it's acidic. So if you have an acidic pH, you have a a low pH, you then would have a high POH and vice versa. If you had a high pH, you would have a low POH. So they are different. Other questions on that? Now, it's also really important to remember this as well. When you're asked a question like, hey, is this solution, acidic, basic, or neutral? There is only one answer to that question. The solution should either be acidic, basic, or neutral. And I say that because when people start calculating the pH and people start also calculating the POH, they make a very common mistake a lot of times. For example, let's just say we calculated the pH and the pH was 4, which would mean if we subtract 14 from that, the POH would be 10. And what happens sometimes when people are calculating both of these numbers and they're asked this kind of simple question of, is it acidic, basic, or neutral? They actually will look at both numbers and go, well, this number is less than 7, so it's acidic. And then they'll say, well, this number is greater than 7, then it's basic. And you basically just said that the same solution is both acidic and basic at the same time, which it cannot be. So you should always, 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 when you're asked that question, is it acidic, basic, or neutral, you should always look at the pH scale and the pH value, because pretty much everybody, this is the scale that people think about. Very few people think about this scale. And so you should always look at the pH value. And again, look at the pH scale and see if it's higher or lower, and to determine if it's acidic, basic, or neutral. In this example I just did, the correct answer is it's acidic because the pH is less than 4. And again, on the POH scale, which is 10, 10 is over here, which also tells you it's acidic. So most people, again, don't have the POH scale kind of in their head. Most people have the pH scale. So when you have these multiple sort of values for a problem and you want to determine, is it acidic, basic, or neutral, 100% of the time, always look at the pH value, and that will help you. That will give you the right answer. Any questions on that? So again, don't be the person that writes, the same solutions, acidic and basic at the same time. Although I don't think I've ever had anybody write acidic, basic, and neutral, but I have had plenty of people write, the thing is acidic and basic at the same time. So only one answer for that question ever, if you're asked that. Any questions on that there? Okay, so a couple important things in terms of relationship between pH and sort of what is happening. The pH scale changes by 1 for every power of 10 that changes, which means if I have an H plus concentration of 1 times 10 to the minus 3, I have a pH of 3. 1 times 10 to the minus 4, the pH becomes 4, and 1 times 10 to the minus 5, the pH becomes 5. So we need to change the concentration of H plus that's floating around in the solution by a power of 10. We will see the pH change basically by 1 unit. And a couple of relationships, as the H plus concentration increases, the pH gets smaller or decreases. Lower pH means it's more acidic. So the relationship here is, as the H plus concentration increases, as we talked about, the OH minus concentration decreases. This is again the acid part of the solution and the base part of the solution. And because the H plus concentration is increasing, we would see the pH go down. More H plus in the solution, lower pH is basically what we see. If the H plus concentration is decreasing, that means the OH minus concentration is increasing, and we will see the pH value go up. And that means that we basically have a lot more base or hydroxide guys in the solution floating around. Higher base part, also a higher pH part in that particular case. Any questions on that? Now, there's a couple of different ways that we can measure pH of solutions. And here's a couple of common ways. We can use a pH meter. A pH meter basically measures the actual sort of H plus concentration that's in the solution. Nice thing about a pH meter is it just slaps it right there and gives you a number. And this is the electrode. Has usually a little kind of glass bulb on the bottom there. You put it in there, does sort of a reaction. Really what this does is it's like a voltage meter. It measures the voltage. You tell it like, hey, this voltage is a pH of 7, or this voltage represents a pH of 4 when you calibrate your pH meter. Then when you go stick it into your solution, it goes, okay, I got this voltage, so that is basically like a pH of 3 or something like that. Another very common way to measure pH is through pH paper or color indicator paper. And basically, as you can see in this picture, you kind of dip the solution on the paper, paper changes colors. You usually have a scale where you try to match it up so all the colors sort of match. And that will tell you, hey, that's a pH of 1 or a pH of 2 or a pH of 6 or whatever it may be. If you ever, tested the water like in a swimming pool, they sell the little kind of tester strips, and it's kind of the same idea. You dip it in the water, you try to line up everything to see, what the values are, and that's a very common way. Another way that we don't necessarily measure pH, but we try to determine if a solution is acidic or basic is we do use what is referred to as litmus paper. And again, this doesn't measure pH, but it will tell us, is it acidic or basic or neutral. So if you have, for example, red litmus paper and it turns blue, that means it's basic. So really, blue means basic. If you have blue litmus paper and you put something on it and it turns red, that means acidic. And again, doesn't really tell you the pH, but does tell you if the solution is acidic, basic, or neutral. So if we look at the pH scale there, here's some examples of the pH scale of some things on the pH. We got pure water, has a pH of 7. Here's some of our bases. Sodium hydroxide, which is a strong base, ammonia, which is a weak base. We can see basic pHs. Vinegar, like acetic acid, lemon juice, stomach acid, and HCl, all acidic here for real. If you measured maybe not pure water and maybe water that's been sitting out for a while, you might be surprised. It will probably be, in this range, the water. And that's because if you have water kind of sitting out, it collects a little carbon dioxide from the air and it makes carbonic acid. Which will kind of increase the H plus concentration and decrease basically the pH of water. So sometimes people are surprised when they put like a pH meter on like water, especially in a building where maybe it's not so sealed or filtered very well. And especially if it's been sitting out for a while, they're kind of surprised, like, hey, it's a little bit acidic. And that is very commonly seen again. And if you need something where you really want the pH of your water to be kind of 7, you oftentimes will boil the water. And when you boil the water, you basically will drive off all that CO2 and allow it to basically come back up the pH to the pH of 7. We talked about this just a second ago. There is a similar scale to pH, which again is the POH. And again, that is the minus the log of the OH minus concentration. Just like the pH again tells us it is minus the log of the H plus concentration. And as we just finished up talking about, when you have both of these numbers, it always is the pH you should look at, because that corresponds to our pH scale that we have in our head as to whether or not it is acidic, basic, or neutral, depending on if it's above 7 or below 7. And again, that nice relationship that I mentioned before, the pH plus the POH equals 14. This gives you a variety of ways to solve some problems depending on your approach. You could use POH, you could use pH, you could use this relationship. You could obviously use our KW that we've used before. And, using some of these relationships, you may not need to perhaps use KW in certain calculations, but you can. Now, there's one more or two more sets of sort of calculations that are very useful as well that we could add to our list here. So we have our KW, we have our POH or pH, our relationship between those. Now, if you are given or you have the pH value, you can get from the pH value the actual H plus concentration from that. And the H plus concentration would be the inverse log of the minus pH. And typically when you do inverse log on your calculator, it pops a 10 and a caret up. How some people do scientific notation incorrectly, but that is what it will pop up. And minus pH. You could also do that for POH. So if you have the POH given to you, you could get the OH minus concentration, which would be the inverse log of the minus POH. Again, when you do that, that's a 10 and a caret minus POH on most people's calculators. So these two equations are very helpful because it can sort of eliminate the need to use KW, but you could absolutely still use KW if you want. It gives you just some variety of options as to how to solve a problem. And they all should get you to the same answer if you punch it in correctly. Let's talk about this guy here, which is the inverse log move. Again, on your calculator, on most people's calculators, upper left corner, you have a shift button or a second button. And somewhere in your calculator below that, you have a log button that will usually have like a 10 and an X on it. So if you were to punch in this, let's say we wanted to do, we had a pH of 5 like we had earlier, and we wanted to figure out the H plus concentration for that. We would do on our calculator, basically the shift or the second button. We would then hit the log button, which if we have a display calculator, when you do that combination, it most likely will pop up at 10 and a caret on your calculator. You would then make sure you make it negative. You go negative, and then you would type 5. Obviously hit equals. And again, if you have a display calculator, that is how you would punch it in. If you have a non-display calculator, again, here, you do need to start with the number in this case. So you would actually hit 5 first. Then you would want to hit the negative button. And obviously you would have a -5 kind of showing. And then you would hit your shift or second button, and then your log button. And then it should give you the answer, which in this case is, where is it on this calculator? There it is. That -5. And if you do that, you will get something that looks like 0.00001. Well, actually, your calculator will probably look like that. We could turn this into scientific notation as 1.0 times 10 to the -5 molar. And you may be wondering why I want 2 sig figs here. I want 2 sig figs here because I have 2 decimal places. So again, going backwards, we go from decimal places to significant figures. If you want to leave it in decimal form, you can, but you really properly should add the extra 0 here. So you have 2 significant figures there as well. And the molarity. Question on any of those formulas there that's on this page. You need to know how to do those and know those, and obviously more importantly, know how to properly punch those into your calculator. Questions on that? All right, then let's do some practice here of these guys and see what we come up with here. I think we got one example coming, I think. Yeah. All right, a couple of different examples here. Let's do for this first one, For the first one, let's calculate the pH. Let's calculate the pOH. Let's also calculate the OH minus concentration. And let's determine, is the first one acidic, basic, or neutral? And for the second one there, let's calculate the pH, the pOH, the H plus concentration, and is it acidic, basic, or neutral? That will give you a good practice with your calculator here. All right, so again, two separate problems here. Calculate each of these things for each of them. Again, try to punch these things into your calculator so you know how to hopefully properly do them. And then we'll all do it here together and make sure we're all on the same page. Okay, let's take a look and see how we're doing here. So I'm just going to rewrite again sort of our list of equations that you could use to solving these problems here. Again, we have our KW, which is our H plus, our OH minus is 1 times 10 to the minus 14. We have our pH is minus the log of the H plus. We have our pOH, which is minus the log of the OH minus. We also have the relationship that the pH plus the pOH is equal to 14. We also have that the pH will give us the H plus concentration by taking the inverse log of the minus pH. And lastly, if we have the pOH, we could get the OH minus concentration. Again, OH, OH, and H, H. By doing the same thing, the inverse log of the minus pOH. So again, there are really multiple ways here you can sort of solve these. So let's take a look at a couple ways here. Let's start with the first one. And again, I'll just kind of go logically for myself here. When I look at the number one here, I have the H plus concentration, which really gives me two options right off the bat. If I wanted to, I could use KW here to get the OH minus concentration because I have the H plus. I also, because I have the H plus, can go right into my pH equation as well. And that's actually what I'm going to do. So I'm going to go into my pH equation here first. And I'm going to go pH is equal to minus the log of the H plus, which would be minus the log in this case of 3.6 times 10 to the minus 9. And if we put that in again, proper like we've been talking about, negative log 3.6 exponent button negative 9, we end up with an 8.44 pH. Now, because I have an 8.44 and the pH value, I can pretty easily get to the pOH from that. And I could get to the pOH from that by taking the pH plus the pOH is equal to 14, which means the pOH would equal 14 minus the pH, which would be 14 minus 8.44, which would get us, looks like a 5.56 as our pOH. Any questions so far on that there? Now, again, I still have the option if I wanted to go into the KW to get the OH minus concentration. I'm actually going to get the OH minus concentration using this. So you can again see how that calculation will work. So I'm going to do that the OH minus will equal the inverse log of the minus pOH. Again, on your calculator, you want to go second button, log, if you have a display calculator, negative, and then 5.56 should pop up something like a 10 and a caret, 5.56 when you do that. And if you do that there on my calculator here, looks like we get something like, again, 2.8 times 10, 1, 2, 3, 4, 5, 6, minus 6 molar. Again, on my calculator, it spit out to me not in scientific notation. And remember, your calculator doesn't always spit out to you the number in scientific notation. Again, you may be wondering why I rounded maybe to 2 significant figures. Again, here it is because 2 decimal places, 2 significant figures, as we're going basically back to that. Any questions on that there? Now, again, to show you that if you chose not to do that, but chose to use KW, should give you the same basic answer. So if we use KW, that would be OH minus is equal to 1 times 10 to the minus 14 divided by the H plus concentration, which is 3.6 times 10 to the minus 9. And again, should really get you the same answer. Maybe slightly off with some rounding, but should be pretty much the same ballpark. And it is 2.8 times 10 to the minus 6 as well. So again, you can see you could use KW. You could use this equation we just talked about there. Either one should work and get you the same answer. Question on that at this point. We still need to determine, is the solution acidic, basic, or neutral? And you really have multiple ways you could do that. You can, if you wanted to, compare the OH minus concentration to the H plus concentration like we did previously. Probably much easier way to determine is it acidic, basic, or neutral is to simply look at the pH value. So the pH value in this case is 8.44. 8.44 is above 7, which means this guy should be basic. Any questions on that there? Again, here, I did not look at the pOH value because that would probably give me the wrong answer. Always look at the pH value. Any questions on how I got any of those numbers there? All right, so let's take a look at the bottom one there and what's going on with that. Same idea. You really do have a variety of sort of approaches you could take. I'm just going to roll with what sort of makes sense to me. Since I have the OH minus concentration, I could do one of two things. Again, I could use KW to get the H plus, or I could go directly into the pOH, which is what I'm going to do. pOH would be minus the log of our OH minus. That goes minus the log of 9.2 times 10 to the minus 2. And putting that into our calculator correctly, minus the log 9.2 to the minus 2 gets us a 1.04, looks like. pOH. Now that I have the pOH, I again could use that relationship that the pH plus the pOH equals 14. Solve for the pH here, which would be 14 minus our pOH, which would be 14 minus 1.04. And that gives me 1296 there on the pH value. Any questions on that one? So here you can see we don't even need to actually use the pH equation. We could just subtract 14 and we do have the pH. Now that I got the pOH and I got the pH, I still have the option to use KW if I wanted to get to the H plus concentration. But since I have the pH, I'm again going to go with this calculation here, just again to show you how it would look. Again, the H plus concentration would be the inverse log of the minus pH. And in this case, when you hit that button, it will probably pop up the 10 and the caret. You want to make sure you make it negative, and you want to make sure that you are using your pH value here, which is 12.96. And if we do that second log, negative 12.96, 12.96 gets us a 1.1 to the minus 13 molar as our H plus concentration. Again, if we went with our OH minus into KW, should get the same thing. And at this point, the last thing that we're looking for is it acidic, basic, or neutral? Again, we have multiple numbers on the table here, but it is the pH that we want to look at. pH is 12.96. That definitely is above 7, which means that this solution would be basic as well. Any questions on any of those calculations there? So it really does, all these equations that are on top there, it really does sort of open up several options as to how to calculate these things. And again, sometimes it's a little quicker to go one way versus the other. But, you know, as long as you choose any of these ways, you should end up in the same spot. Any questions on that? Okay, then why don't you try maybe this one? We got a pH of 5.67. Let's do what is the POH like it asks. Let's also do H plus, OH minus, and again, is it acidic, basic, or neutral? We're getting to the end here. Let's take a look at this one. Again, based on all those formulas we just seen and we've been using, you do have a variety of sort of options. So to me, since we have the pH given to us, it would make sense perhaps to get to the POH really off of that. And again, that's using this relationship that the pH plus the POH equals 14. That means simply the POH would be 14 minus our 5.67. And in this case, that would get us 14 minus 5.67, gives us a POH of 8.33. Any questions on that one there? We also want H plus and OH minus. So in this case, I could get the H plus concentration from the pH value. And again, that would be the inverse log of the minus pH. Again, when you do the second and log button, probably will pop a 10 and a caret up. You want to make sure that you do make it negative. And here, since we're looking for the H plus, we want to make sure that we are using the pH value here. And that would get us 5.67. And if we do that, second log, negative 5.67. Again, in scientific notation, 2.1 times 10 to looks like 6 minus 6 molar. Again, on my calculator, did not give it to me in scientific notation. All the zeros, 0.00002138. Other option at this point now is, because we do have the H plus concentration, at this point we could use KW if we wanted to get us to the OH minus concentration, where the OH minus concentration would be 1 times 10 to the minus 14 divided by 2.1 times 10 to the minus 6, and 1 to the minus 14 divided by 2.1 to the minus 6 gives us, on your calculator, you probably have this number, which is 0.8 of those, and a 5. If you happen to have your calculator there in scientific notation, you would get a number like 4.8 times 10 to the minus 9 molar. Again, your calculator ran out of digits. That's okay to leave it like that, or turn that into 5 times 10 to the minus 9 would be okay as well. My calculator ran out of digits when it wasn't in scientific notation. You also obviously can do the inverse log of the minus POH, which would be 10 caret negative 8.33. And again, should get you to that number as well. And again, it may cut out in terms of zeros on your calculator. And you may kind of bottom out there at 5 if you're not in scientific notation, and that's okay as well. Now we do want to determine, is it acidic, basic, or neutral? Again, we have a number of questions on here, but it again is the pH we want to look at, pH being 5.67, which means it's less than 7, which means it is acidic in this case. Any questions on any of those sort of calculations? Any question on how to calculate pH, POH, H plus, OH minus? You obviously do need to know how to do all these calculations. And for most people, again, it's just making sure you understand how to properly punch them into your calculator. It's half the battle there. And also making sure you know which one that you want to use and sort of which application. So remember, as we talked about earlier today, you know, pH, POH, H plus, OH minus, they are kind of different things, but they are related to each other. And they're just sort of a different way of displaying sort of the same information. So, you know, if you're looking for a concentration, either KW or what we just did here towards the bottom. If you're looking for a pH or POH value, then that's where you go minus the log of those things. Any questions on any of that? Okay, we will then stop here.